Okay, so with a little bit of calculus, we can actually derive a lot of really useful equations and formulas from this Cobb-Douglas production function. Remember, this is the Cobb-Douglas production function, which basically tells you that output is going to be labor times to the raised to the power of A times capital raised to the power of B. The first thing is, how about this marginal rate of technical substitution? So we just said that the marginal rate of technical substitution, which is the slope of the isoquant, right, it's going to be equal to the ratio of the marginal productivity of labor over the marginal productivity of capital. So how can we derive that from this equation? Well, remember that this is very similar to this utility equals xy. And remember how you divide the marginal productivity of x and the marginal productivity of y by taking the partial derivative with respect to utility for each one? It's the same thing here. Remember that we're using the same function with just simply changing the variables. And marginal product is nothing else than, well, by how much output would increase if I increase my labor by 1 while holding k constant, which is exactly a partial derivative. The slope of L to k, assuming k stays the same. So if we use the partial derivative of output with respect to labor, we will actually find the marginal productivity of labor. And for this equation right here, this is going to be A times L, A minus 1, k comes down as a constant. And we can actually find the marginal productivity of capital in the same way. That will be the partial derivative of Q with respect to k, which will be B times the constant times KB minus 1. So these are both equations for the marginal productivity of labor and capital. And since we know that if we put them on top of each other, the ratio of that is in fact the marginal rate of technical substitution. So we know that the marginal rate of technical substitution is going to be what we just found was the marginal productivity of labor, all right, over what we just found was the marginal productivity of capital, which is B L A K B minus 1. And the cool thing about this is that we know that we can simplify this by taking the A minus 1 exponent of L, bringing it down with a negative sign, and taking the B minus 1 exponent of K and bringing it up with a positive sign, and the result of this will be A K B L. So we just found a very simple and useful shortcut to finding the marginal rate of technical substitution for any Cobb-Douglas production function. So when you need to find the Cobb-Douglas, the marginal rate of technical substitution, or the slope of the isoquant for any isoquant of the that has the Cobb-Douglas production function, you know that all you have to do is to find the values for this equation. So if you know the exponents, for instance, are A equals B equals 0.5, then you know that this is going to be equal to K over L, because the 0.5 will cancel out. Or if this is actually equal to, if you have different values for A, if you know that A equals 0.2 and B equals 0.8, then you know that this is going to be equal now that the slope of the isoquant, or the marginal rate of technical substitution, is going to be 0.2 K over 0.8 L. And you can do that directly. You don't need to do all this partial derivative, because at this point, we already found the equation for the general case. So the first thing you should know is that the ratio of the marginal productivities, which is the marginal rate of technical substitution, is going to be equal for any Cobb-Douglas production function. It's going to be equal to A times K over B times L. And the next thing we're going to do in the next video is to find the output elasticity for this Cobb-Douglas production function. So we're not done, but I'm going to break this video into two so that you have some time to digest this stuff. It's a lot of math here, but we're trying to find shortcuts, right? So at the end, there will be some payoff for you.